Greetings, healthcare colleague. My name is Ken Kocek. I'm the founder CEO of Chemical Q Device. Today is May 11th, 2023 for discussion number 82 for discussion on quantum backends. So these are software and are basically simulator and hardware-based ways of running quantum programs with this. There's always more out there in quantum that you would ever expect. If you do a thorough literature review and, all across the web and hardware and simulators, what's kind of like grabbing my attention right now is these Amazon quantum simulators. Now, I know Amazon doesn't come across too often in this group. It's typically you have to pay for it, and it's it's an on-demand service. But the simulators they do have, they say they're concurrent with up to 35 tasks with one of them. So I'm not sure if that means 35 notebooks. So if you're running a circuit, quantum circuit or hybrid program, how many exact duplications of code that means. But anyways, it seems to be a little bit more robust than some of these other ones out there. So you can run on, say for instance, PennyLane. So you have default.qubit, you have lightning.qubit, you have, I think it's default.mix. I typically use default.qubit. And that's as far as I know, that runs on a CPU. Now, the other news I found this week is basically this, is that NVIDIA, or actually Tom's Hardware, believes that GPUs will remain the front runner in front of real quantum computers for a while. So this is a May 4th article. I'm going to put that in the chat there. And it makes sense, right? Because you see all these other quantum simulators and, there's an emphasis on getting results from these, smaller qubit circuits using simulators. So I thought that was kind of interesting. And, it's going to take a while for the hardware to turn the corner. So, until that time. So for instance, so Google has TensorFlow Quantum, and everybody knows it for Cirq. So Cirq is spelled C-I-R-Q. And the newer one is called QSIM. So it's QSIM. So in the actual TensorFlow Quantum, the paper, it's like a 55-page paper. They go over all of the benefits that QSIM has over Cirq, mostly with speed. And in specific, it uses, it's called gate fusion. So gate fusion is basically, you have a bunch of gates, it pre-multiplies before you're running your main, quantum operations right there too. So that's kind of interesting. And then IBM has a whole host. So there's state vector simulators, there's, it just depends on what you're trying to do, density matrix, those types of things. So as a startup or anybody that's looking for faster results or even better results, because sometimes you can get better results with one simulator versus another, even though they're noise free, it's the way that they do it. It's the way that they process the quantum algorithm. So, for IBM, they just have so much material, and you can watch one YouTube video after another, and it'll give you exact instructions as far as, say, for instance, in hardware. Before I get into hardware, I kind of want to get kind of like a feel for that as far as, what everybody else is using or is interested in. So I just went over a bunch of the simulator stuff. Any questions or comments with that, in regards to the simulator aspect of that? And it's definitely, yeah. So yeah, we have Azure Quantum as well too. So, and I'd be interested to know as far as like, what exact benefits people are getting from one versus the other, because in my experience, it's just trial by error. So if you're this specific quantum simulator is doing this thing with the manipulating gates at first, and you're getting better results and faster significantly. And and for those that don't know, so it's like Python, right? You learn the first code, and then the second one's not as hard. So I did catch one of those. It was it was a Q hack. So they use Q sharp. And it's different notation, but if you know what you're doing, I think there's definitely commonalities, between all these different quantum programming platforms as well too. And then, yeah, so anything else on simulators there before you start to get into hardware a little bit? Hardware is talked about ad nauseum, and I'm not going to lie with that. I talked about it ad nauseum. I brought with me a little, so I'm on Linux here. It doesn't like the drag and drop. I'm going to post in the chat basically some reviews I've done, or basically it updates, so your IonQ and Google and what they've been working on. But it's one of those things, like if you're working in academia or if you have a startup, you want results fast. It doesn't really matter. Well, it matters, but everybody wants to scale. And I wrote down, and basically my summary between the two is simulators. You do noise free on smaller circuits, smaller qubit counts. And obviously with a quantum computer, you can get up to 433 qubits, and it's fast, right? So these simulators are slow, and you're looking to scale. So it's a more prospective experiment that you're doing with a lot of the hardware, as opposed to like I say, we run on a 127 Eagle for IBM. This is running well, and then when the next one comes out, or maybe we'll bump up to the 433 Osprey when it's more available, then we'll go that approach. And plus you can say, hey, we just ran on, real quantum computer. So that's the thing with it, is a lot of this, and I heard two analogies just recently, is it's still kind of, and I think Ron maybe mentioned one of these, maybe still in the, vacuum tube stage of, the technology, the real hardware. And then the other analogy, it was a Q2B. So this is QCware. It was one of their recent events. And they basically said that, it's kind of like the Wright brothers taking off in the first plane, those types of things. And after looking at a lot of the specs, I have a hard time arguing against that. So Ron had put it in the chat, has anyone used the Eagle? Yeah, I've known an individual that had a circuit ready to run on it. I know it's up and running because at that QCware conference, they put a 127 qubit map up, and that's what they were working on in specific. So, I think it's like with most of the other hardware in experimental stage. Now, in comparing all of these, and I mentioned Tom's Hardware, is there was a 2021 hardware analysis of, ion trap versus superconducting qubit and so forth. I think those are the main two. And basically, your maybe IonQ was one and Quantinuum was number two. And then I haven't seen any other updates since that, besides they said with the GPUs kind of, will be at the forefront. A single GPU will be at the forefront for a while, as opposed to like a quantum computer. And I think that's mostly because the air and a decent number of qubits probably too. So yeah, I mean, Eagle, and other people can come in on this too, is, Eagle's been out for a while. I think Osprey, the 433, was supposed to take over. And I think, at least one person in this chat and other people too have found that, it's not really available yet. I can't access it, on my, so if you do like a least busy in Qiskit to find out which computers are available, those types of things. So yeah, it's interesting because, it's trying to solve a specific problem. And right now the simulators are doing that, right? Because they can finish these experiments. The other thing I learned this week is so when you get these printouts, from Qiskit or from whoever, is you get probabilities. Now probabilities, even if it's supposed to be 50-50 and you're getting like 53-47, that doesn't necessarily mean that it's error or fault. So ERROR, or faultiness. That's why you run more shots, is to equal it out. Now, when you start to see a bunch of the other probabilities boost up, that's more of a telltale sign of there being error in the system. And then as your circuits get deeper and your qubits get wider, that is, it gets worse and worse. It perpetuates all throughout that circuit. So that's the issue there. But it's just one of those things. You'll learn the most if you just run on these, because if you're reporting results and then, you need to know exactly what is going on, even if the results, especially for real hardware, aren't quite there. So I put into the chat here. So this is a couple of those, hardware experiments that are basically looking at, the developments. I know so Quantinuum, so again, we're talking about backends here, so quantum computing backends. So in the hardware section, Quantinuum just announced this week, they did, I think it's 35 qubits with a GHZ. So GHZ is a fully entangled circuit, maximally entangled circuit. And I wasn't sure as far as full availability. They call it the H1-1, I believe. And then so that hit the news too. So I was also listening to this YouTube video, and feel free to chime in as we transition here, is basically if you're into software and quantum, they're basically also specializing in hardware, because what they're programming has to match up with is, what's available to run on. And I thought that was kind of interesting too. So it's really not separate, even though I focus on software, most of the time. So any questions or any comments in regards to the two? So we talked a little bit about the simulators, and there's more to talk about with both of these too, and talked a little bit about the hardware as well too. And I know in specific, people are coming from GPU, CPU backgrounds, and I'm also kind of interested because there's multiple fronts with this whole GPU, either being the quantum simulator or helping the quantum computer kind of thing, because that's their DGX for NVIDIA as well, is basically using GPU technology to assist quantum machine like a real quantum computer with the error that it has. So yeah, any other, I guess, kind of updates with that? It's definitely an emerging field, but there's cool stuff you can do. So without getting too much into software, you can switch the embedding layers, and that makes a huge difference in the results of your parameterized quantum circuit, and it's running on these days quantum simulators mostly, but it's trial by error for sure. And the literature, go ahead, Ron.
I was just going to mention that Quantinuum had some other news that just popped up in the last day or so, related to some research regarding anions.
Uh-huh.
Has everybody seen those things go by? And basically, just read a quick blip from this. Anions are quasi-particles that exist in 2 dimensions. They are not true particles, but instead exist as vibrations that act like particles. Certain groups of them are called non-abelians. And so the word abelian, I'm not sure if they're using this term in terms of mathematical sets. I'm not sure what that means here, but they say that non-abelians are cool. Prior research has found that non-abelians have a unique and useful property. They remember some of their own history. So based on that, I'm also going to guess that some people are going to indicate that that might lead to quantum memory. But what they're saying is it should lead to quantum machines with much less noise. So don't quite understand all of the physics of that, but I had wondered not that many months ago if a breakthrough in quantum mechanics, such as some new particle, might come and save the day. Maybe this is it.
Yeah, I appreciate you bringing that up. I think the biggest thing is if it was quantum memory. So that's being addressed anywhere from Google with their superconducting qubits, bringing in some form of, this to help out the quantum computer with its error with that. And when I was looking at LinkedIn, some other company actually, they recommended this Quantinuum article that you're mentioning. And I think actually they might have mentioned the 35 qubits, the gigahertz in that paper. If not, maybe it was 2 papers. But it's just good to hear because what are we, May? Yeah, May 11th, going into summer, figure some people cut off like investors June, July. I think especially like July 1st, basically. That, and there'll be some cool summer projects too, for sure, in quantum, from small startups all the way up.
Yeah, well, I think this anion thing could actually manifest itself as true quantum memory particles, as opposed to some of the other techniques that are used. Quantum memory is it's really a bad term because basically what it seems to mean to a lot of algorithms is that you can tuck away the state of a particular qubit or qubit register for a period of time. And so they call it memory, but it isn't. You can you can still only read it once, but after a period of time, you can bring it back into a qubit or something like that, but you can only do that once, and then you can do your measurements. But this thing that they're talking about, they might actually have the ability to do it more than once if the particles have a memory of what they have done in the past. So it's a very interesting concept. Again, I don't understand all the mechanics. Haven't gone and read the paper on it yet, but I think it's quite interesting that um, some theoretical particle may be the key to into a vast improvement in qubits.
Yeah, I mean, my guess with it is it's a little bit further along, for this established company to basically post on that. And a majority of these papers, if not all of them, are archived. They're not peer reviewed, but some of them do make it to Nature. So, like I said, I was listening to a fair number of talks this week, and it seems like no matter what hardware technology we're talking about. So Ron was talking about ion trap. There's gate-based superconducting qubit. There's neutral atom, silicon spin, and photonics. And maybe a couple others, but they all fall under the same category as they want to be scalable. You want high coherence between qubits, low error. And they were mentioning one of them because they said some of the technologies, or at least one of them, has had a high coherence, but it had an issue with reading algorithms. So say, for instance, like superconducting qubits is known to have a lower coherence, but we're running these circuits, OpenQASM, through their circuit composer, or you can, basically port in or import through Composer Lab. So it's interesting because the one that'll make it will be the one that kind of checks those boxes off the best. And I would say, and we've talked about ion trap a lot, and they might be leading right now because based on papers, funding, and also plans to scale up, hardware manufacturing facility, IonQ, first half of next year. So and there's dark horses. So the dark horse is silicon spin, but you'll hear from them and they say they have potential for billions of qubits, like theoretically, have that potential. And they're saying other technologies won't reach that point. But, it's interesting because it's all about application, right? Because you can use ion trap quantum computers, and they've used in literature, even in Nature. There was a quantum GANs paper in Nature, and there was another, I think it was polymer analysis paper with ion trap with IonQ as well. And you'll see Quantinuum in there too, I believe, at least not just arXiv, but maybe Nature as well. So yeah, but that's the thing, right? Is because like it's hard to know if you just look at home pages, and then if you go to these talks. I haven't been able to go to, I've been referencing Q2B, which is QCware's big conference with several hundred people that go to it, and we've had members that have been to that in person, and they'll say up front, it's like, oh yeah, superconducting qubit struggling here, but this other one has great coherence, but it's has problems with the algorithms, with the software component of it too. But between all this, the ones you hear about the most is definitely the ion trap and then the gate-based superconducting qubit as well there. Any other comments on this? So we had talked about, we had touched on several of these. So mostly hardware, and then I started off with quantum simulators. I put something in the chat there as far as like some slides, and just be interested how much people are running, because in order to run on something, you need to know the back end simulators, the cost, performance, availability, scale up, these types of things. And like I said, we haven't really talked about AWS Briquette, but their quantum simulators seem to be maybe a tick ahead of the curve compared to your average free simulator that you use maybe from Qiskit or PennyLane. So, it's definitely the application. And I wouldn't run 35 experiments all at the same time, through this. They say it's their AWS DM1, which is density matrix, and SV1, those are their more state vector. I wouldn't run like a lot of experiments without testing out, figuring out how it works. And then, okay, I want to do this set of experiments. I just need additional information. And by the way, they have a TN1, which is 50 qubits and a circuit depth of 1,000 or smaller on a tensor network. So these quantum simulator kind of these specs, and then the IonQ, their financial report for most recently, I think it was actually, they just came out with the one today. So it was the one before that. And I'm sure the hardware's only going to get better, or that's the trend. And they said that they can do a 25, qubit Monte Carlo algorithm, and it's not going into the yellow or red, it's staying blue, basically, in that. So, that's just my take on it. And it, basically with this is like, it's not just hardware, it's not just software, because if you design hardware that isn't based on, TensorFlow Quantum and, Qiskit and PennyLane and Microsoft and QSharp and all these platforms, is that it's, there's no use for it. So it's really, and even I think IonQ said they need more on the hardware side, just getting the computer to work, and they're better off on software. But it just depends on the company. So, and then feel free, anybody that we haven't heard from. I saw a number of people, or a couple of people come on. So Anand or David or Hang, go ahead. And then, if you haven't gotten to that point, I would definitely get there as far as running. So running experiments, that's what I mean. And I'm on Colab now using a NVIDIA V100 GPU on standard runtime. I've used an A100, but I haven't found any better results, and actually it took a little bit longer. So it just depends. And their free service will not cut it for you. If you're doing machine learning, because essentially I'm doing machine learning, and at the end it's a quantum classifier. So that machine learning part is done on a ResNet convolutional neural net on a GPU, and then the quantum circuit is ported over to the PennyLane, like a default.qubit type of deal. And it just seems like there's a lot of room for growth with this whole like GPU simulator stuff. And when I read Amazon's, the DM1 and the SV1, this is definitely sounding like GPU territory as well. So, but I'm interested as far as like, what other people have run on, or if you haven't gotten started, feel free to ask a question. Like what's a quantum gate, what's a circuit, what's the best circuit to run in this specific application. I know for image analysis that there's at least two. So you can use a quantum circuit on the convolutional neural network, which is basically the deep learning part, and the majority is still classical. And then I've been doing, it's called quantum transfer learning. So that's more like the your quantum algorithm is at the last step, and you set your output to whatever. And so you're either binary classification or your multi-class classification. And then, so those results have definitely been promising. So, I mean, besides speed, right? Because it just takes longer on this. I call it maybe like first generation quantum simulators, as opposed to like what I've been talking about with the GPU outpacing the quantum processor, that kind of stuff. And, any other companies could, so David had mentioned Microsoft, and I haven't done a ton of research with this. Maybe I looked into it very early on in the startup. So this is more like they were ahead of the curve with algorithms. So this is, basically a ruthenium catalyst turning CO2 into methanol and water kind of thing. And they did the paper. The paper was great. And at the end of it, they said that they just need like 1,000 logical qubits. So, but that's not happening quite yet in order to do what they wanted. Okay. So the moral of the story is they could do that experiment because the ruthenium catalyst is small, and this catalytic cycle is all small molecules. They're not like polymers, big, biomolecules, those types of things. And they were very thorough, great supplementary information as well. And I definitely read it once and then kept referring back to it. So the other more of the story is that these big companies have stuff not disclosed, because that was one of the projects they worked on. It'll be interesting to see, it's just, if somebody comes out with big news, just expect it in the next couple of days. It's not a coincidence kind of thing. Other startups and other big companies too with quantum. And then, so David also said, quantum software will rule for sure. And, it's a broad field. So my perspective is in quantum and then machine learning. So nothing like images and so forth, the training data is not being done primarily quantum. That's still classical. And then, so for instance, like these two cases I've mentioned, the quantum part is either classifying, or the quantum part is helping out with sliding this window over an image. And then say, for instance, it'll map individual pixels to a qubit, that kind of stuff. There's an IBM tutorial for that. But that's the big thing. Maybe 99% of the people don't realize it's not really quantum machine learning yet. It's quantum parameterized quantum circuit. And then you have the machine learning, and the PQC is helping out the other classical parts. And, I would say it's just moving past first gen, because in image analysis, there's been 6 or 7 papers between brain tumors, dementia, COVID-19, pneumonia, retinal images too. Most of them binary classification. So there's one multi-class. I did a multi-class too. And, it's moving into, it's sounding like more of this, GPU environment kind of outpacing things, maybe on the real hardware part. Yeah, so Ron, I think this is for you. So, and you could come on, Ron or David. IBM does a lot of stuff. So they do summer, I don't know, I haven't heard the one this year, but I know last year's was, there's summer school was error correction school. The year before they did one, I think it was quantum machine learning in 2021. And I think they've done at least 3 straight. So yeah, Ron says he's signed up for it for sure. And if anybody, especially new, if you're listening to this on the recording, is basically start off with Qiskit. It's all free. You can get like 7 qubit, QPUs, maybe a little bit higher now. You can draw your own circuits. You can, if you have Python skills, you can program in Qiskit Lab. And I've been catching these, 1 minute or 2 minute clips on YouTube. Super helpful. One of them shows you basically how to show which of the backends, simulators and real hardware are, least busy, and it just gives you the least busy. This is probably available other places too. Another one's kind of cool because it'll show you how many qubits above your threshold. So if you say ba 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 ba, and then do the code, qubits above 6, it'll only give you about the quantum computers that are available to you on your package based on pay that that you can use. So it's a marathon, not a sprint kind of thing, because you learn all these little tricks. And say, for instance, you found a simulator or hardware on a different manufacturer that makes your code run faster, better performance, those types of things, and it could really help out too. I will say, so I did miss the Qiskit last Friday. They usually have it Fridays. It's 9 a.m. Pacific, so it's 11 Central, and then that's noon. And it's usually an hour, and it's super technical, like mostly quantum error correction kind of stuff. Go ahead, Ron.
Yeah, the one that that I saw today is just one of their short bits. It wasn't one of their live seminars. I'm looking for the it's in the Qiskit channel on YouTube, and it was just released, I think, today. It's only a couple hours old, and it's a short 4 or 5 minute thing, and they talk about the IBM Challenge, the IBM Summer School, which they say hasn't been scheduled yet, but there's a couple of other things they talk about, different things that are going to happen over the summer and the fall. So it's only a few minutes worth watching. If I can find it, I'll post it.
Yeah, appreciate that. And I would say to those listening is basically don't think that you have to get your awesome project done. It won't happen. You have to take baby steps, small wins along the way. And with that is that if you're coding, like most code, like that's written in Python or whatever that I get put into Colab or Qiskit or a local Jupyter Lab notebook, is it's still in Python. It's just there's one block of code that's dedicated to quantum, but you need to know how that works, right? So if you want to change your embedding layer, if you want to switch, so I was just dealing in literature, the craze right now is CZ gates instead of CX gates, or CX gates or CNOTs. So it's basically entangling two layers. But you'll see a lot of CZs, like high performing algorithms, like from MIT, that you have a layer of Hadamard gates, some CZs, and then like what was it at the end? It's either an RY. So you get these from the paper. They don't always work with classification. So there's no like universal algorithm. And what I found is just making small tunes to your specific one. So I published on this. It's the third iteration of my MVP. And what I found is basically that the embedding layer, as opposed to the other 2 or 3 layers, played a huge part in accuracy, and loss. So then I took that, and then I basically narrowed down, what is the most optimal, quantum circuit out of these 9 for angle encoding. And then I did another one for amplitude encoding. And the amplitude encoding I had to kind of retrofit in, because I have for loops and all this type of stuff, because it's not listing each individual wire and gates. It's a for loop like you'd have in Python. So getting all that stuff, and actually in amplitude coding, I get a significantly faster run that actually has pretty good, it's not the best, but performance, accuracy and loss. And then I'm going to further develop that. And it's an iterative process, right? So you learn so much by things not working, and then, try to stick to literature, YouTube instruction videos, technical ones that are related to you, papers, all that kind of stuff. But yeah, I mean, at this point, that's definitely what it is. It's a marathon. It's it's not a sprint to you have this awesome circuit, plug it in, you have great results. It really is an overtime job. Any other kind of questions with this? So we've talked about kind of the performance factors. We've talked about simulators, hardware, those types of things. And then I think Ron put it in the chat there too. So this is the whole Qiskit. So people that are in Qiskit, and I'm kind of like running whatever model suits the task that I'm trying to perform, which is based on papers and all this kind of stuff. And I just got back into Qiskit, but it's great to start. And I've heard that quote before is, start with Qiskit, get your feet wet, run some circuits on quantum hardware. If you can code or even do blocks of code, do something productive. They have tutorials. So they have quantum machine learning tutorials. I've done a bunch of those, or 3. So yeah, it's a great first step for sure. And PennyLane, which is where I wind up the most often, their models. So their models are based on authors that are using the PennyLane framework. So you'll see this, QML dot, that's them. And they also have their gates sometimes aren't truncated. So you'll have a C naught instead of a CX, and then you'll have a dot Hadamard instead of a dot H. And that's the least of your concerns. So Qiskit was behind with machine learning. And then they had this thing called Torch Connector. Now, Torch Connector allows you to get into PyTorch. And then that solved a lot of those problems that people were having in basically having to use PennyLane. So say if you're primarily doing neural nets and Qiskit, those types of things, you have access to Torch Connector. I don't know if that was by plan or if they were forced to do that, but as far as what I've heard and listening to other people talk at an end of the video, they said our problems are solved because now we have Torch Connector. So, and things will start to, in my opinion, start to firm up a little bit as far as like, okay, use this exact thing, use that. You will see a lot of, PennyLane code and literature for sure. So PennyLane, I think they were first launched in 2018 or 2019, one of those two, and they beat everybody else by like 2 years. And then you have like, Qiskit actually was, they didn't have machine learning, I think, in 2017. So they launched first, but then they came out with Qiskit machine learning after PennyLane. And then, 2020 was TensorFlow Quantum. And then 2022 early was Torch Quantum. So Torch Quantum appears out of the 3 of them the most kind of like, for lack of better words, you're hacking into it and using Torch Quantum on a very fundamental level with PyTorch as well to come up with something fundamentally awesome, whereas the other ones seem to be more like higher level. And, as far as resources and kind of which direction you want to go, because a lot of people, like say, for instance, like PyTorch got big with Tesla and then, other big companies too. And, they all have a story, and that platform more than likely was, got built up even as Tesla was using it. And, it may have morphed and changed to suit preferences. And, it's going to be a similar type of thing with quantum, because it's like, TensorFlow Quantum is Google's, and then they have Cirq. So people are really into Cirq and then importing circuits. And now they have QSIM simulator. So you know what I mean? Like you're in that environment. You're not stuck in it, because a lot of times you can do, be agnostic with hardware. But as far as like that's just where you are. You're using Cirq, Google's version of this. Any other last questions or comments? So, it's fine. If you haven't really gotten to that point where you're just like running every day and, reading papers every day and YouTube videos, that's fine. Go ahead, Ron.
I was just going back to look at Colab. Were you saying that you were running some QML stuff through there, or just
So it's this quantum transfer learning model that's primarily, so it's trained on ImageNet, and then it's trained again using a GPU on ResNet. And then at the very end of it, it's a quantum classifier, like binary. You could set out to whatever, 2 or 4 or whatever. But yeah, I mean, it's not really quantum machine learning, because it's not like the machine learning isn't doing the image part in these tasks. It's just too much for it, like a quantum simulator. But the quantum part is the parameterized quantum circuit. And like I said, there's 2 applications that I found for that, like that are actually, seem like they're working.
So those are quantum simulators. They're not connecting you to Google's quantum resources. per
Yeah, so
se.
it's a penny lane code. So every time I
Okay.
start that notebook, I have to import my drive. Just a heads up for those using Colab, don't use don't use the folders on the left. You have to just use your drive because it gets rid of everything when you go to terminate the kernel. So I have to do that, and I also have to install PennyLane every time I do it too, and then I hash it out, and then I'll keep running.
So that was just an example that you got like from the Penny Lane
Yeah, it's called Ants and
domain.
Bees.
Okay.
So they did an Ants and
Gotcha.
Bees PennyLane, so you could search for that, or it's Quantum Transfer Learning, and it's one of the, if not the only one that put the code. So I modify the code to if I want to make it multi-class, or if I want to insert brain tumor images or improve performance, modify batch size and epochs and all that kind of stuff.
Gotcha. All right, thanks.
Yeah, and don't be I mean, it's still mild, the quantum impact of it. If I take away the quantum layer, it doesn't work in this case. Some you can take away the quantum layer and it'll tell the difference. So in other models, the quantum layer seems to be helping with loss at lower training image sizes consistently, but then accuracy with or without the quantum layer was, usually prefer quantum, but not always. So, as far as the level of quantum advantage, right? Because even if you claim you have great results, how does this look, without a classical layer or without the quantum layer? Yeah, and I would just,
sounds good.
the notebooks, a lot of them are on GitHub, like I said, but Andrea Mari, Mari, it's a gentleman in France, and he's put up a number of notebooks that I've used, and he uses PennyLane code, and I think he works for PennyLane, and they tend to just work, like it can get annoying if you have these promise work notebooks that take significant fixing if you're not an expert in that specific area. But it works in Colab. I can't get it to work on this laptop locally or on my local Jupyter lab, even though I want to because it's faster, but then I don't have the GPU that I have in Colab. So there's trade-offs. And then Qiskit, I haven't quite got it to work yet, but it wasn't really designed for Qiskit, even though you can import PennyLane. So it's meant to be agnostic, but if something's like, it's basically either, tensor, if machine learning, it's either TensorFlow based or PyTorch based, one of the two. And then in mine, it's PyTorch based with the with PennyLane. And then you're running their quantum simulator and it, abides by its rules of setting up gates and whatever you want to use the quantum aspect for. But, for those out there, it's, if you've had hard times with long sections of code, which all these notebooks tend to have, the quantum layer is typically a lot shorter. And then, with limited knowledge, you can make modifications even without knowing what it was going to do fully. And, it's not that bad. It's not like writing brand new code. You know what I mean? Because if they already have the block filled out, then you can, change things and change epochs and, batch size, your training images, validation set. And, just don't get discouraged.
Yeah, that's pretty cool that Colab gives you access to GPUs for free.
Yeah, like I said, they
Yeah.
have a TPU too. I didn't mention that today. Tensor processing unit. I didn't do a full study on it. It didn't seem to be any faster. With my
Well,
notebook,
it depends on what they're using for GPUs. The latest and greatest NVIDIAs have tensor processors as part of their GPU chip.
oh yeah, I
So
came across that. Huh.
which is one of their ways of trying to keep the things busy. You can load up a task in the GPU, one of the GPU's tensors processor as an abstract. It's basically you just it sounds like you just pipe code over to it and just let it fly.
Yeah.
And so you don't have to, but you still have the issue of getting the data moved in and out of the graphics realm.
Yeah, they have
But
their basically data frame, like
they also,
they're go ahead.
the newer NVIDIAs also have service modules, which are like um, closer to CPU cores, as far as I can tell. I mean, most of the operations that go on the GPU are very primitive, but it can do a bunch of. They have, the GPU cores are just like the graphics cores. Um, they're basically they can do floating point operations and not that much more. Whereas the service modules are like a higher, or like a more like a CPU core, but not quite a CPU core. Where so again, you can load code into it just once, and you don't ever have to deal with that again. And the service modules can apparently manage the the tensor modules and the graphics cores with like being hands off from the hosting PC. So again, depending on which GPU they're giving you for
Yeah.
free, you may be getting tensor cores. So
Yeah, I mean, you could start off free, but you'll quickly realize it's just way too slow on a CPU. And then, so it's $10 for 100 credits a month. Okay, so every month they're gonna ding you, and then that gives you 100 credits. And then you can also spend everything's that same. It's a credit $1. So like if you want to, I've had to pay like $30 so far with all this stuff, which isn't bad, based on all the work that I'm doing. And for that one, it's just another 100 credits for another $10. And then the level up is $50 for 500. So it's the same per credit per dollar, but then you're getting access to even better GPUs. So I'm still on the $10, and then as I need another 100. The A100 on their GPUs really drains your credits. So I would definitely do all your testing and all that stuff on the V100. And then I usually use standard runtime. But you can on a V100 go up to the high RAM. So that makes like the interface faster. It's the CPU part of it, I think. And then on the A100, you only have one option, A100 with high RAM. And it's like a $7,000 GPU at least. But when I've run on it, like I said, it didn't make anything faster on my circuit. Well, actually, it would have been used for the ResNet layer, ResNet 18 for medical images. So I still haven't figured that out. Like it should have helped because I know the quantum circuit the GPU doesn't really touch because it runs on the PennyLane simulator, their default .qubit. And yeah, like I said, make sure to mount a drive. Don't create your own folders in there because you'll lose them, because it'll tell you you're going to lose them too after your session ends. And then, like I said, if you're importing whatever, it's like every time you open a new notebook, like say if you have a notebook, you have a certain performance with it, you go to open it, and then you have to mount your drive, install PennyLane. That's the only thing I have to install on that one. Not every single time I launch open Colab in a tab, but if I'm running consecutive experiments back to back to back, I don't have to mount the drive. I don't have to import PennyLane.
yeah, I'm guessing there's probably a way to connect that to Google's cloud services again for a small fee, so you don't have to do that each time. But
Yeah, you're probably right. It's just a 2-line code, and you probably well, I don't even know if you'd have to pay for it to auto load it, but it's not a huge deal because I'll do back-to-backs a lot. But when you start, just if you're doing the V100, you shouldn't have an issue with it just rapidly draining your credits. But if you do the A100, you will.
Sounds like something fun to play with.
Yeah, I would definitely get into do notebooks that already work well, and then make modifications, algorithms. If it sounds like you've been reading, what can you substitute for this embedding layer? What could you substitute for the CNOT gate? Do you like the pattern of the CNOT gates? The tricky part is a lot of these things are like in for loops. So if you're good with for loops, then you'll know what your CNOT gates exactly mean or how to change them, if you have a better idea based on literature or other things.
Well, it's going to be pretty difficult to swap out CNOT gates. It's like one of the primitives that pretty much every machine does. But
Yeah.
I think what you're referring to is how you get one loaded, or there are variations to it. Get one loaded in your circuit.
Yeah. I found this old paper and it was all written in CNOT gates. So CNOT gate is a 2-qubit gate and with a control and a target between two wires. And then they said they put into like a parenthesis, they said it was a Grover's one, and they said put in parentheses Toffoli gate. So then I took that whole section and then based on like the pattern of it, I put in a single Toffoli gate into Qiskit and I got better results. And actually, plugging that into what they wanted. Actually, no, I used their circuit and then used my modified circuit, which is the single Toffoli, which is a 3-qubit gate. And, because they were limited in hardware, they couldn't do based on that. I think it was a superconducting qubit. They couldn't do a 3-qubit gate at that time. So it's interesting. And I guess one of the things that we haven't touched on is quantum algorithms have not been run on awesome quantum computers yet. So we don't fully know if they will work. Grover Search, which is the one I've been referencing, there was a paper out there within, I think, the past month, and they believe that based on the architecture of the quantum computers, that it may not scale. And they actually probably went further than saying just it may not scale. So I like to focus on the things that are working now, especially with simulators, small PQCs, all this stuff with cybersecurity. Sandbox AQ just got $500 million. These algorithms, and I believe this is how it works, is that they're all NIST algorithms, one of these four. And all these companies like Sandbox AQ and like QSecure and more, they're using those algorithms. And then that's the hard part, is turning it into an application for clients that want security against potential quantum attack. But the actual algorithm it doesn't change, right? It's not proprietary. And, that's, looking at all this stuff, that's the way that seems, is it's going to be, these smaller quantum algorithms run on classical hardware to defend against quantum defense. So you have to take all this and say like, okay, this is working, this might work, or those types of things. You're weighing all these scenarios basically. And there's actually a federal law that requires all federal agencies to implement these PQC algorithms, which are similar to the ones that I've been using. They're just smaller quantum algorithms on, simulator. And I want to say it's by this summer. So anyways, there's going to be some news coming up because, that deadline is going to be, expiring. NSF says we're still supposed to have a practical quantum computer this year. And slowly but surely. But I think the biggest recent news, and we talked about this at first, was the Quantinuum, their recent hardware. So like Ron said, with the abelians and anyons and all these, and then, around this time, or if even in that same paper, 35 qubits with a GHZ state, which is 3 people's last names. and it's a fully entangled over 35 qubits, which is not typically seen on a real quantum computer. So even on a simulator, that would take forever. So yeah, so definitely some good news, this week, I would say. And any other questions, Anna or Ron? And then kind of like where you are in your journey, and then, anything you would like as far as, to help. It's a very broad field, right? So, the QEDC, this committee basically, or a consortium formed from NIST, which was from, presidential order several years ago, is meant to bring companies together so they can figure out things, even though one's working on this hardware, those types of things. It's a very collaborative effort, I would say. And if you join one of their calls and stay on towards the end, you'll hear, we need this, it was a quantum internet talk, or, basically Aliro and others. And they say, okay, we need this to work, and we need this to work, and there's a moderator. And, the gentleman's like, oh, okay, we'll do this and that, it's building up together kind of thing. And then anything else? So, most people don't know a ton about quantum, and then, they view it as a nascent technology. I wouldn't call quantum simulator. I'd say that they're different because it's quantum mechanics on a classical, or, GPU, CPU kind of thing. So, what's the distinction? And more than likely, you have certain tasks that'll be run on a quantum computer. Oh, the other thing too, serverless. And you probably know about this too, Ron. Serverless or multi-cloud computing. And that's kind of, I'm doing it on a very tame scale, but like my quantum simulator is wherever PennyLane has it, this classical device. And then, the GPU is wherever AWS has this. So that's going to be the other part too, is like when companies, they do a specific task, and this is like thousands or, hundreds of thousands of dollars, to do it more efficiently, do this part of the code here, this part of the code here, all in the cloud, meaning, and I believe that's what that term means, is serverless now, meaning like you don't own your own server kind of thing.
Yeah, that's become very prevalent, especially with quantum, and some other terms that fall in line there, microservices, or services as a platform, and just, the general development of APIs. So your program is running somewhere, but it's got connections to resources all over the internet. Like you said, wherever PennyLane's big monster simulator is parked, you just talk to it via an API.
Yeah.
So it's not so much that it's serverless, it's like server, I don't care anymore. So
yeah, I think they put a term on it, right? Like QSaaS, right? Like quantum computing as a service.
well, yes, software as a service is one thing. Software as a platform is another thing, where your what you think is a platform, you're just talking to through an API.
Yeah.
So this is like what goes around comes around, because back in the day, you would never put your hands on a server. You would connect to it over the comlink. It's just basically the same stuff with bigger toys, I think.
Yeah, it's interesting because I probably don't have to know how exactly all this stuff works, but I have to know my program and the specific parts, like, oh, this is over in AWS at this, split second, and then it gets sent over here. And then, because you find stuff out and say like, oh, okay, why aren't you doing it like this? And there's, a data backlog or something like that, and you could do a different way or switch to a different device. And, these types of things. But it came up in a different conversation too, as far as like regulatory and simulators and, quantum computers, is I don't even know how much quantum simulators, which is basically quantum mechanics, running a quantum algorithm on a classical or GPU, how much additional regulation they would need for medical, right? It's a different type of processing technique. Like you have superpositioning inside a GPU, say, and then you're having interference and entanglement and all that kind of stuff. So, it's just, I think it's probably like a new software program, right? But probably a little bit more than just switching from like Google Sheets to PowerPoint. You know what I mean? Like it's the data is processed in a fundamentally different way, even though it's still on a CPU or GPU.
Yeah, well, everybody should ditch all their Microsoft stuff. That's just me. Anyways, I have to pop out, so it's good chat.
Awesome. Yeah. Well, this is discussion 82, May 11th, 2023. Talking about all the different approaches to different quantum computing backends, so simulators and computers. Appreciate everybody coming on. Enjoy the rest of your night and have a productive rest of your week. Take care.